Hello, welcome to Node Spaghetti. My name is Joseph. Today I've got a tutorial for you about blending normal maps together with node groups in Blender 2.81. So in this first example, I've got a cloth object that uses a separate set of textures for the seamless part of the cloth and the seams. This is a very simple example. Let's look at a little bit more complicated example. In this example, I want you to imagine that I'm working on a level for a game, and the final design has not been set in stone, so we might have to make changes later on down the line. Now, I'm lazy. I don't like to repeat work. So the way I'm going to go about doing this is I'm going to make a procedural material using several different seamless MIDI materials and blend them all together into one quality material with all kinds of different materials within it. Like this right here. We get good results from this. It looks almost like I cared enough to paint things by hand, but I didn't. This is all procedural. It reacts to height. And I could even go in and paint details if I wanted to make one area more rocky or one area more grassy. Here's what the mask looks like, colorized to make it look pretty. And you can see I'm mixing the albedo map, the specular map, the roughness map, and the normal map. Another advantage to doing this procedurally is if for some reason I need to add another mountain, maybe the level has expanded or something, go over here, model a new mountain, and we're going to pretend like I'm making a much better, more detailed terrain asset. Simply unwrap it again, and there we go. Because this is using seamless textures, we can also bake out the details and save it to a texture. So we don't have to send this procedural material into the game engine, we can save out the result of it too. We could even add another landscape using a generator like ant landscape. You can see we get a lot of work done for us for free this way. I've got one more example for you. So in this last example, imagine that the game that I'm making has got a level with a bunch of antique statues in it. Maybe it's a museum or a Roman courtyard or something. So I've gone online and acquired this 3D scanned model of an actual sculpture. I got it. I'll put a link to where I got it from in the description. I can't redistribute it, but you can download it for yourself and play around with it. The director of the game has asked me to make several different versions of the model with different types of stone materials. Marble, rough stone, granite, for example. Now, obviously, this object is far too high poly to put into a video game. We'd use up the entire polygon object in just a few of these statues, and we've got an entire courtyard to put these statues inside of. So what I've done is I've used the quadriflow remesh in Blender 2.81 to quickly make a medium low resolution version of the statue. And now to get the details back from the high poly object, I simply bake the normals from this onto this. Now there's a problem. What I want to do is add a normal map for different types of stone. Now if I simply mix them together using a mix node, it flattens out the details from the bake. And the effect is particularly pronounced with these stronger normal maps. Can't even see the high poly details when you're using this one, which might be what you want and it might not be. But in this case, I want to have those crisp details and the normals from the texture, from the seamless textures. So you might ask, why not just bake the normals from the high poly object with the normal map applied. And you can see that looks great. We have all the detail from the high poly normal map and from the seamless normal map. But as you can see here, that's in the texture itself. We really don't want that because now we're going to have to bake it out several times for each of the seamless textures. And if we have to make any changes to the sculpture later on down the line, that's just going to be a pain. We don't want to deal with that. Because actually to bake the details from the high poly to the low poly, I had to spend a lot of time editing the baking cage to get it just right so that it didn't create any weird artifacts when I baked it. And I don't want to keep doing that every time I change the model. What we really want to do is we want to find a way to layer the normal maps together so we get the full effect of each one. And at this point, the director of the game walks in and he says, okay, I just showed your low poly model to the tech guy, and he says that that's still over the polygon budget. So we need you to make an even lower poly version of the model. So I run it through the decimate modifier a couple of times, and I wind up with this, which you can see here. And unfortunately, now the details from the high poly sculpt do not look good on the low poly object. And that's because its shape has changed, so the relationship between the two surfaces at each point is very different. So we can remedy that by baking the normals from the medium poly object onto the low poly object. And that looks nice. But we still have the problem where we try to blend the different layers of normal maps together. Now the reason why simply mixing the normal maps doesn't work very well is because normal maps are, after all, a mathematical means of producing an effect. They are vectors. So each pixel in the normal map is a direction. And if you treat it like a color, you're going to get the wrong results. You have to treat it like a direction. So I have gone ahead and I've done a little bit of research. And if you've looked into this problem before yourself, mixing normal maps together, you've doubtless encountered this article because this is the go-to resource for solving this problem. And there are about 5 different ways of blending normal maps together that are presented in this article. And I have made each one. I'm going to show you 3 of them because 2 of them are kind of redundant. The first method of combining normal maps, which is pretty common, is the overlay node, which is built into Blender. We don't have to do anything. I only made it a node group to make it consistent with the other ones. We don't have to do anything to get overlay, and it gives us pretty good results. What the overlay blending mode does is, if the second image is darker than 0.5, it multiplies the 2 images together. And if the second image is lighter than 0.5, it screens the 2 images together. And that happens on a pixel by pixel basis. And it works well enough for the red and the green channel because the farther away it is from 0.5, which is neutral gray, the stronger the effect of the normal map. Now, unfortunately, overlay is used for textures, for combining colors, so it doesn't actually consider the geometric vector mathematics behind the normal map correctly. So, while it does give you pretty good results, and it's certainly usable in a pinch, I've used it before, and if you don't care about getting it perfect, and you don't have time to deal with all these node groups, just use the overlay node. It works well enough. But there are better ways. Here is the partial derivative blending method. Look especially at the fingers and the face. Back in overlay, partial derivative. Overlay, partial derivative. You can see the PD blending method gives us much nicer, crisper details. The second method is rotation, which tries to take the detail from the base texture and rotate it on, or it takes the detail from the base texture and tries to rotate the details from the detail texture onto the base texture using Euler mathematics. and it works well enough. It's not 100% mathematically accurate, and it gives a slightly different result from the PD blending because it actually makes a distinction between base and detail. So you'll get a different result depending on which one is on top. Anyways, you get a different result depending on which one is on top. But it's very subtle, almost indistinguishable. That's the same thing with this reorienting normal maps method, which again I've taken from that blog post that I mentioned already. This is one of my favorite ways of blending normal maps together because it's 100% mathematically accurate, and it's the same method used in Krita. And I'll just show you really quickly. Let's open a couple of normal maps. But you can see that it doesn't simply blend them together or overlay them, it combines them, and you get the effects of each one. I used to have to do this in Krita manually if I wanted to get correctly combined normal map textures. And the way that I found that article to begin with is I tried to find out exactly how Krita blends them so I could re-implement it in Blender, which is what I've done here. It's the same algorithm, it gives you the same results, and now you can do it procedurally. Awesome. And because we've got these ways of blending layers together, layers of normal maps, this is the wrong way to do it with mixed nodes. And you can see just how bad the results are of doing it simply by mixing. Similarly with overlay, we lose detail with each layer, but with the mathematically correct way of doing things, we keep the detail in each layer. I've got one more example of why you want to blend normal maps together correctly, and this one is especially fun, in case you're wondering what all these modifiers are for. I've gone ahead and rigged up this effect that breaks the statue, because if we're making a game with lots of different statues, we're going to want a few of them to be different than the others. And the great thing about this is that it automatically adds cracks in the place where I break it because of some of these modifiers I put on it. And the cracks are blended into the normal map, as you can see here, so that I don't actually have to add geometric detail. And it gives us a really nice result. And now we can have several versions of the statue that are broken in different pieces and scatter them throughout our game level. So we don't get tired of seeing the statue over and over again because it's a little bit different each time. And it's really easy to do, doesn't take a lot of effort, and we can get lots and lots and lots of good results from it. So I think I've done a sufficient job of showing you why you want to do procedural mixing of normal maps. Now I'm going to switch gears and talk a little bit about how they work, in case you're interested in that. And if you don't like math, if you don't like dealing with nodes and all those noodles and stuff, just go ahead and skip to the end of the video and download the node groups from the link that I've got in the description. But if you are interested, keep watching. So the first thing we need to do is understand what normal maps actually are. We all know what they do. They cause the surface of the object to react correctly to the light depending on what direction the light is compared to the surface. And that's really great. We get awesome results with very little effort. But what exactly is the normal map? What do these weird bluish-green colors actually mean? The way to understand it is they're vectors. Each pixel is a vector. And the vector points in a direction relative to the tangent space of any particular point on the surface of the object. Tangent space is what I'm demonstrating here with these three arrows. See how the blue arrow always points directly away from the surface? The green arrow is always perpendicular to the surface, and the red arrow is perpendicular to the surface and to the green arrow. The blue arrow is called the normal vector, the green arrow is called the tangent vector, and the red arrow is called the bitangent vector. So the red channel of this image is a value along this red bitangent vector. The green channel in the image is a value along the green bitangent vector. And the blue channel in the image is a value along the blue normal vector. So the thing about vectors is they can be either positive 1, between 1 and 0, negative 1, or between negative 1 and 0. There are any number of values between negative 1 and positive 1. And generally, you want each component of the vector, the x, the y, and the z, to add up to 1. The absolute value of each component should add up to 1, that is. Now, a color can only store positive values because it's meant for images. It's not meant for vectors. That's unfortunate because we need the full space between negative 1 and positive 1, but now we can only store 0 to 1. So what happens is the color data goes from 0, 0.5, 1. The vector needs to be negative 1 to 0 to 1. So the normal map maps the value of 0 to negative 1, the value of 0.5 to 0, and the value of 1 to 1. It crunches the data of this long strip right here down into the space of this not quite as long strip so that you can store a vector as a color. Let's take these three lines to think of the color channels, red, green, and blue. Instead of the vectors, let's think of these as the channels in the normal map now. Because the normal map is a single vector with 3 components, we need each of these 3 components to add up to 1. So when the green channel is long and the blue channel is long, the red channel has to be really short. And when there is some green and some red, the blue channel has to be short. When the blue channel is long, we need these to be 0. Similarly, if those are long, we need the blue channel to be 0. And that's what we see if we look at the channels. We see that where there is red, or where there is green, there is not blue. And that's actually the only purpose that the blue channel has in the normal map, because it always points away from the surface of the object. And we already know the normal, because Blender calculates it just to give us flat shading in the viewport. It's not actually very useful to store in the texture. So what the blue channel does is it's there to keep everything normalized, and it preserves the relationship between the length of the green and the length of the red relative to the original normal. So let's open up the statue again and take a look at how the normal map node groups work. The first node group scales the normal map. Let's take a look inside of this. And we're going to ignore this part for now because I'll explain that in a second. And just focus on these values. What we're doing is we're taking the arc sine of each of the red and the green channel and the arc cosine of the blue channel. Then we're scaling the vector. Then we're taking the sine of the red and the green channel and the cosine of the blue channel and combining them again and normalizing them. Why are we doing that? Well, every time we have a sine or a cosine or a tangent or anything like that, we have a triangle. And in this case, the triangle is between the tangent and the normal, or the bitangent and the normal. Either one works. We don't care about the triangle between the tangent and the bitangent because it doesn't matter. It stands to reason that the more similar the vector is to the normal of the object, the weaker the normal map is because it's just the regular normal. But the shorter the normal vector is in comparison to the tangent vector, or direction, rather, it's all one vector. But it has a magnitude along the tangent direction, the bitangent direction, and the normal direction. Now you can see that the strength of the normal map is proportional to the length of, or the magnitude of the blue, the z, and the green and the red, the x and the y. They're legs of a triangle. And that's why you see the arcsine and the sine, the arccosine and the cosine, is because what we have here is a adjacent and a I never actually studied trigonometry, but it's because we're dealing with the relationship between the legs of a triangle. When this leg is long, this leg is short, and when this leg is short, this leg is long, and basically the flatter these two triangles are, the stronger our normal map is at that point. Now let's take a look at the partial derivative combine normal map node group, because this is the one that isn't explained in detail in the self-shadow blog article, and it's also the only one that I really can honestly say I understand the math for. So the first thing we do is we take the base and the detail texture, and we multiply them by 2, and we subtract by 1. And the reason for that is because we're going from this space to this space. So if we, from the color, right? So if we multiply the color by 2, now 0 is mapped to -1, 1 is mapped to 0, to 0, 1 is mapped to 0, and all the way over here we've got 2 mapped to 1. We don't want that, so we simply subtract 1 from it, and now -1 is mapped to -1, 0 is mapped to 0, and 1 is mapped to 1. So once we unpack the color channel into a vector with the full vector space, we can separate the channels, and what we do is we take the x and the y of the first texture and shorten them by the z of the second texture. And we take the x and the y of the second texture and shorten them by the z of the first texture. That way, they have the correct proportional relationship between each other. And then you simply add the x and the x together, and the y together. And that's almost good, but now that we have the x and the y channels of each texture proportional to the z of both, we need to shorten the z in each texture so that the proportion is correct in the final output z also. And then, because we've shortened the z channel, and we've shortened both the x and the y channel and then added them together, what we need to do is normalize it. And that will map everything between -1 and 1. Finally, we multiply it by 1/2, and then we add 1/2. And that gets it back into the same space as the color, which is what the normal map node is expecting. And there's a couple of other methods of combining normal maps in the paper. The rotation method, which rotates the map by 90 degrees in the x and y direction, and then uses the z channel of the detailed texture to choose basically how much of the rotation to use, and then adds them together. And the orientation method does something similar, except instead of using Euler rotations, it uses quaternion rotations, which are a lot harder to understand, especially for somebody that is an artist and doesn't do a lot of math or programming or anything like that. So I'm not going to attempt to explain it because I don't really understand it very well myself. You can read about it in the Self-Shadow blog. The math is carefully explained and derived and simplified. And I'm using the simplest form of that, which is right here in the sandbox example, for the node group in Blender. And if you really want to understand the math, you should read the article because this guy understands it a lot better than I do. And the reason why I went through the partial derivative method piece by piece is because he just glosses over it in this article, because that's not what it's about. It's about this reorienting normal map method. This is the most mathematically accurate method. This is close. And the partial derivative method is the best if you want it to not matter which one is the base and which one is the detail. There is one more set of node groups I'd like to show you, and we're going to open the terrain file for that one. So right here, I've gone ahead and made a simpler mask for mixing two normal maps together. And this is different than the statue example, because what we're doing here is we're not layering them, we're blending them. So instead of combining them together on top of each other, we are sort of feathering them into each other. And the pink part of the map should have one texture, and the blue part of the map should have the other, and the part that's sort of gray in the middle should have some of each. So I've got two different node groups that do this. The partial derivative method, and because this one is commutative, it doesn't matter which order you put the two textures. This is a very simple way of doing things. And this particular node group is designed to give you good performance when you're using a lot of them. So instead of bothering to scale the normal map mathematically correctly, I'm simply mixing it with blue. And let me show you real quick. For each texture, I'm mixing the pink part of the mask with 0, 0, 1. Remember, this is crunched down in space, so 0.5 is mapped to 0. This is just the normal. So wherever the mask is pink, we mix it with the plain original normal, and that has the effect of scaling the normal map down to 0. And for the other texture, we need the blue part of the map to be 0 and the pink part to be 1. So we invert the mask by subtracting it from 1. And any color value, and the mask is a color, blue and pink, right? Any color value is going to be between 0 and 1, so subtracting it from 1 has the effect of inverting it. That doesn't work for vectors, but since the mask is a color, it works just fine. Obviously, you can't multiply the color by -1, because then you'll get negative numbers, and we can't have that. So in the second texture, we simply invert the mask and then mix it with the flat, simple normal. And then we can do the PD blending method, because it doesn't matter what order the textures are in, and we get a great result. Now, if we wanted to be 100% mathematically precise and layer the textures on top of each other in the between area, we have to do it a little bit differently. Since this one is meant to be mathematically precise, I've gone ahead and used the scale normal map instead of merely mixing it with the original normal, which is essentially the same, but it's a little bit more correct if you're really a stickler for those details. And honestly, there's really no reason to be, but sometimes you're too much of a perfectionist to just let it go, you know? So I've got to reorient the normal map once for each texture so that it can act as the base, and the other texture can act as the detail. So in the top, the bottom texture is the base and the top is the detail. And in the bottom, the top texture is the base and the bottom texture is the detail. And the result is very, very slightly different. In fact, it's so slight that it's indistinguishable. Well, it's not indistinguishable, it's almost indistinguishable. And then we do the PD blending between these two, and because that adds them together, we scale it down by 1/2. And this gives us a very slightly more mathematically accurate result. And it's a slightly different result. Oh, in fact, let me just fix that real quick. There we go. Now we can compare them directly. And you can see there's almost no difference. If you're obsessed with the tiny details, you might find that one of them gives you a better result. So I've included both of them. Anyways, that's all the node groups that I've made, and there's a download link in the description of this video. So that's the tutorial. Let me know how I did. Let me know how I explained everything. Let me know what you learned, what you'd like to learn. My purpose with this channel is to present all of this information with the understanding that you're a professional, you've got things to do, you don't want me wasting your time with a bunch of stuff you don't need to know, and explaining things that you already understand. Because I think you're smart enough to figure out a lot of this stuff yourself, but you're also busy. You've got a job to do, and you don't want to have to research everything carefully. So I'm trying to do the research for you and help you to understand everything as correctly and accurately and specifically as possible, and also save your valuable time by presenting it as clearly as I can. And I'd like to have a lot of this kind of content on my channel because it's something that I think is hard to find on the internet, and it's especially hard to find with a consistent level of quality. There are so many tutorials out there, but most of them are for beginners, and if you're a professional who's got a limited amount of time to spend on research, you've got deadlines, then you don't want to waste your time with a bunch of beginner tutorials, even if there is a nugget of useful information in them, because you're on a time crunch. So let me know if I've succeeded in that goal in the comments section. Please go ahead and share this video to your friends that have an interest in procedural materials. Give it a like, give it a favorite, put it on a playlist, subscribe to my channel, all that stuff, if you think I deserve it, because I would like to continue making this sort of content. So thank you very much. This has been Joseph with Node Spaghetti, and I'll see you in the next video. Or, well, you'll see me in the next video. You'll see my blender. You won't see me. You'll hear my voice. I'm gonna shut up now. Thank you for watching.